All right, let's look at this Clippy paper. There's like improving training stability for multitask ranking models in recommender system, and it leads to optimizer called Clippy, Clippy anagram or anagram Clippy. So this looks like a recommender paper, but it actually uses YouTube's recommending video model as example, but but in essence, it tries to solve a problem like loss divergence, which is pretty universal, happens in lots of places. You can see this like the problem they are facing is on the YouTube recommendation. Sometimes they do multimodal learning, which is try putting in audio, video, user history, maybe other inputs simultaneously. They try to understand all the parts, like every essence about the user, the video, and with all that understanding, can have better recommendation. But loss divergence happens. Saying they have micro divergence and full divergence. So this is the area under curve. The higher the model performs better. This is the loss. The lower the model performs better usually. And this spike isn't good, right? Because for a moment the model isn't behave very nicely, and this spike, this dip isn't very nice because yeah, that's basically the same thing. This is called micro divergence, which is not very detrimental to the model. As you can see, as the training goes on, everything goes back to normal. And but this moment is full divergence. Full divergence, so it has micro divergence, the full divergence. Full divergence is somehow cannot recover to its pre-divergence value as training continues. As like the model becomes total retard. Like it's no, not worth to say. We just you might as well just start to train a new model. So this paper tries to solve this problem. It also mentions, okay, of course you can try to build some sort of pipeline or control measure to not release this model if it doesn't comply to certain metrics, but it still has hassle that you have to actually have to spend time and resources to train this model. If you are throwing away this thing so frequently, saying like when they are trying to put more and more objectives and more inputs, this happens more frequent. I guess this is why the reason for the paper, and you just want to control it from the source. Find why this thing happened. It happens to more easily things what, and what can we do to solve about this issue. So this paper discuss this finding the problem, finding the source, and try to solve it. What's the previous solutions to that, and what's their solution step by step. Okay, it says the cost of issue. The cost of issue is you know if we look at this chart, it's a very famous chart. As like this is the normal training. You try to solve a convex problem. That is, you trying to find the bottom of this thing. So if you're training this way, it's like getting healthier and healthier when you are here, and you start iteration, and you find it's not close to the truth. It use gradient as pointed direction to the to like how you can travel down the path, and it travel down here according to some learning step. That means is the size of the step. And since you are closer to the truth, that means your gradient will be smaller. Your next gradient will be smaller, and you can just travel down and down and down and down, and getting closer to the truth by each step. But divergence happens when if you look at this, if you the first step too large, and if you observe this dot and this dot, you will find this dot is like further away from the truth. That means the gradient will be larger. The next step will be larger. Okay, so a step here and a step here and a step here, like keep bouncing around, until it totally slide out. That's like when the paper claims, okay, this is the source of the loss divergence. and it talks about like in what situations this can happen. Mostly for them, the three situations: data distribution changes, saying like you are digesting a lot of cat videos or mostly music videos, then suddenly a day you seeing videos introducing about cars or history stories. So this will be totally different. Like the entire understanding of the world might change so sudden, so the model doesn't come back anymore. And a larger model size and complexity also contribute to the problem. Multiple objectives and single objective. As multiple objective, this is some technique I first heard of, like when it's in the competition about the shark. It's like when you're trying to solve this problem, it's like a very simple classification problem. But also, if you try to guess as other targets, saying that you want to guess what boat you are on for this picture is captured. It's like very satellite tasks, like not important satellite tasks, but trying to guess that as output instead of putting it as input is somehow a technique that will make the model understand more of the situation. Like it will try to have better focus on things that might give you a clue. So this technique has its like drawback. Like when you back propagate through the model, saying one of the objectives is very wrong. Say you not only you're trying to guess the rank of recommendation, you also trying to guess the score of some certain performance, but that guess is very off at sometimes, and the this very specific objective is trying to back propagate through the entire model, like the rest of the objective, like the first, not the first, maybe the top shared layer. That means the last shared layer might absorb quite a shock that also might lead to a loss divergence. So with all these reasons, these are all the reasons like behind the motivation. If you can solve the loss divergence, we can have all the nice features mentioned here, like more objectives or more complexity in the model. Um, okay, let's see how it defines some of the problem and try to solve it. So this is what I love about this paper. It tries to pinpoint the problem by looking at the moment when the crash happens. So during the divergence, this is like divergence happens on step B. The loss certainly spikes up to a point that never returned. This AUC dip down like it never returned. It's the same chart we've seen. We've seen here, except it looks closely only on these steps, and it defines tries to figure out the problem and how to improve things by defining three terms like step A, step D, and step C. This step A not happen, step B happening, step C after what has happened. And it also look at the top hidden layer of the model, which is in this case is like more closer to the objective, I guess. When we're looking at things, it did experiments using AdaGrad, which defined here, saying when you have this sort of thing, you might want to say scale it back a little bit back by the cumulative gradients. That's when every time you have gradients, you do the square, put it into the accumulated pool of gradients, and you this minus means it's dividing the square root of accumulated gradient. So this is the update times the eta, which is the running rate, which is like how you update the weights from wt to wt plus 1. So this is basically the optimizer, right? So it defines two ways to mitigate the loss divergence problem. One of them is gradient clipping, GC in short. So when every time it mentions GC, it's gradient clipping. Others adaptive gradient clipping. Okay, to look at all these things, like what does it do? So gradient clipping and adaptive gradient clipping, what they do is it try to scale down the gradient before the optimizer. So this steps happens before this steps. So this steps will try to change this gradient. So after it changed the gradient, you have new gradient value for this updating the accumulated gradient thing. Um, so yes, so all these like GC and AGC, they happens before the optimizer. So let's see how they update the gradient. You don't have to update the gradient if it doesn't matter some threshold. So what is threshold? Threshold is if the magnitude of the gradient is larger than some lambda. That means say uh, when we are looking at this, sometimes the gradient gets bigger and bigger. But how about like we know the magnitude of this gradient, because we are going to use it. We are going to use it in the other gradient anyway, because you can see this is like a plus with the square of the thing and divided with the accumulated square root of this thing. So this is basically L2. So what it tries to do is like, okay, it tries to use this L2 thing, L2 of the L2 norm of this gradient as the magnitude. It's not like considering each element of the gradient tensor. So this is a tensor. But this is a scalar number. This is full number. The L2 norm is a scalar number of the entire gradient tensor. So this number measures, how is the magnitude of this thing. If this is huge in some level, we want to scale it back. It means like we divide by this thing, right? We divide it by this full number. So you can see we'll have new gradient, which is much more friendly, that we can try to update with the other graph. So this is gradient clipping, and in other cases it's like a gradient norm clipping, or because there's also some gradient clipping that we just do the actual clipping. We are like if the gradient is magnitude is larger in some way, we just cut it. But this thing is like trying to scale it back. Okay, adaptive gradient clipping. So this thing has certain setbacks, like you have to scale or fine tune this lambda thing. If you fine tune this lambda, say if you have a linear layer or batch norm layer, this lambda can be totally different. As if you want to scale down things, the gradient is it actually huge or not huge? It's certainly depends on the weight. Say if you're looking at this, if you say if my weight is all in scale to close to zero, it's like 0.1 as their magnitude, like it's like around their range of magnitude, but your gradient is 0.2. That is pretty huge update, right? It would totally screw up the layer. But if you're just some linear layer, your weights are somewhere around, say, mostly like 1 or even 2. Your gradient is 0.2, the same. But in this scale, it's not that huge. It's actually pretty timid and mild. You don't want to clip it too much, right? Because you want to have the fast update, like let the model learn everything quicker. So so in this situation, we are like let it portion by the weight. So this is also scalar number. Like if this is the like I mentioned, if this is the like magnitude of the gradient 0.1, but the weight is the magnitude of the weight is also around 0.1. This will be a very huge number. That means we want to do the clipping. But if this magnitude of the weight is in proportion to the gradient, it's like a sorry, the L2 norm of the gradient is in proportion to the L2 norm of the weights is somehow very friendly. In that case, we don't want to do the clipping. So this thing is more adaptive. It's like a more adaptive to the G. Sorry, more adaptive to this weights. So you don't have to set up this lambda so flexibly. You don't have to fine tune this lambda so frequently. Yes, this is AGC, this is GC, AGC, and AGC also happens, like I said, before adaptive other grad happens. It just fine tune the gradient. So this paper is saying, okay, if you look at this chart, so this chart is about say if you look closely at step A, step B, and step C, this chart is about two things. That this is measurement, this is like a clipping factors. So this is the measurement. This is the measurement. You use the measurement to see if we need to do the clipping. If measurement is like a larger than some sort of lambda, we want to do the clipping. If the measurement isn't, doing so, like we are just keep the original gradient. And clipping factor is like the scale back how much factor. It's like we want to scale back by this thing. Scale back by lambda divided by like the L2 norm of the gradient. Um, so they call it like clipping factor. Uh, Clipping factors. So this is basically the clipping factor of GC. This is a GC. This is the Clippy, which is invented by this paper. If you look at saying is this is measurement. If the measurement is larger than some atomic number of this thing is larger than some lambda, we'll do the clipping or not. So we want this thing to be pretty sensitive to things as we can discover when we need to do the clipping as soon as possible, because on the step C everything is lost, like we don't have the model anymore, uh, and we want this thing to be say whenever we are trying to do the clipping, when the loss divergence happens, we want this scale down factor to scale down as much as possible. So this is a very small number. Like it can scale down a lot for the Clippy, what this paper has invented. But for GC and AGC, we found like GC scale down some, AGC scale down a little bit more, but none of them are enough, as this paper has discussed, as like if these are enough, we don't have to have this paper, right? So this paper proposed the Clippy, which it claims it can scale back down a lot when the loss divergence happens, and it can detect this loss divergence like better when it requires. So okay, this is like how this whole thing works. Like whole thing works for the previous research. For Clippy, it's saying like the previous research doesn't work in two cases. Sorry, in two reasons. One reason is say it's using L2 norm. L2 norm is like I said, is a scalar flow number. This scalar flow number. This is a scalar flow number, which doesn't represent like some small portion of element that might be has huge magnitude has huge absolute value in their own term. Saying if you have a very sparse tensor, most of them are close to zero, like one or two of them they are really high, like something like a 5 or -6, you don't even know, but the L2 norm isn't much, so it won't be triggering it's not that sensitive, it won't be triggering um, the clipping. So if you look at this reason, what it does is it's not using L2 norm anymore, it's using infinity norm, or Chebyshev norm. Yes, it looks complicated, but it's just like you take the maximum value of absolute value of all the elements within a tensor. That's like if we have a tensor, you have the you just take the largest magnitude out, like absolute value out, instead of doing some sort of norm operation. That's like giving more attention to spiky single elements instead of like overall situation. And also it also says something like instead of working on this gradient, because GC and AGC, they like this step, like they are worked before they add a grad. But after you tries to do the optimization are its own funny steps, funny things might happen to the actual updates. So why not using the actual updates, like RT as the thing you want to work at instead of gradient. So you're not scaling down gradient, you're scaling down the actual updates, which is more close. It's much closer to the actual effect. So there is a paper actually discussed about this idea that you're using update instead of the gradient as the clipping measurements and factors. The paper somehow I mentioned it's like the lamp paper, but this paper also discussed about like you're using L1, sorry, you're using infinity norm and combined with this like I'm lost here. Sorry, combined with this like doing the scale down on the updates part. So this is the update algorithm. It mentions this is pseudocode for you get a gradient. This is a step that belongs to add a grad. This is calculating the update. Okay, then it uses updated to calculate the sigma. Sigma is the scaling factor. With all those things, you can see apply rescale updates. Yes, and you reapply it to the weights and you update the weights. So this is part that I actually got confused. Like it's not like I'm questioning their method. It's just like when I'm trying to see how it works, like I try to build my own stuff. Okay, let's see my code first. Like when you are in the Clippy, sorry, not Clippy. Here let me start from here. Yeah. Okay. I built a pseudo data set that will output random features, fixed random. It's like for every category, the feature is going to be somewhere around the same with some sort of like a noise input. And what I do is like I do training to guess what category it is, and in one of the steps saying in one of the step like yes, I just like output fixed random features with some noise, but when train the model, let me see. Oh, when train a model, I have a step like when the step is while the distribution, that's saying like when this like I want to do disruption on the data distribution. That means like whenever I want to disrupt, I like reversed all the features, so the model will be somehow seeing totally new different world with totally different answers, and it will try to it might try to do a very large step, and when I want to try to visualize the whole thing. So this is like what we don't do with any of the remedies. I guess this is a like not like full divergence, because it's really hard to replicate full divergence. The thing that I can run on my laptop, it certainly cannot like so far as I tried, it's really hard to repeat. But as you can see, like in a lot of steps, like I only damage it for a single step, but for a lot of steps it cannot repair itself, like until like later on it relearn all the accuracy to its previous level. So then I try to gradient clipping, that's say like doing the same task, and you see before the optimizer step, I do the clip grad norm. The function is defined here, which is just basically trying to, if the measurement is the L2 norm of the gradient, and if the measurement is larger than certain lambda, I use this lambda divided by the grad norm, exactly like the paper described. Let's see. This is like what I do is like if measurement is larger than the lambda, we do times this and divide by this, like to scale the whole thing. Of course, it has certain health. Like if you look at the charts, you will still find, yes, this is like the measure actually spikes up during the event that I said, like 1800 as the step that disruption might happen. It's very sensitive to that actually, and this is the accuracy. Like accuracy, like suddenly suffers uh, less disruption. It's like because when the divergence happens, you try to scale the updated step back. That means you can have much less damage to your model when the distribution of the input changes. Then the adaptive gradient clipping, which is the same. There, you have two norm like grad norm and weight norm, exactly like the paper described. Also trained the same, but like with much longer, sorry, with the same steps, and you can see it also works in some level. Um, and okay, so the problem I'm having right now is saying, okay, try to duplicate how fancy this Clippy is, because at this step, um, this is the algorithm says on paper, but what I can have is I find this thing is really hard to replicate. Maybe because like I didn't like fully duplicate the full convergence issue, but also this thing is different from its original. Sorry, this thing is different from the official code deployment. So I found their like original. Sorry, I found their official code deployment. Um, it's saying the TensorFlow right now. Um, so many things they are different in variable names, of course, but even in some code. So in the paper you can see it says it's still doing like a GT times the accumulated gradient. That's like a minus power is divide, right? It's like dividing this square root of the accumulated gradient, but on the optimizer, it's not what it does. It's doing, say, yeah, it's like a precondition is square root of this. Okay, the square root it used to, the delta is LR times grad value times precondition, and it uses delta as the you know, as this RT part we mentioned in the paper. So this is one major difference. The other major difference is you can see um, in this paper it says like when the weights is kind of small, like it's small in the magnitude. If you are all close to zero, it's much closer than it's much closer than the GC, because everything is close to zero. It says it's much closer to GC, as the only remaining value will be like a very small lambda value, which is like this part will be close to zero. This part is close to lambda value. So if you look at this thing, which is like only scale back by lambda. Only scale back by the update that's close to how GC works. If you look at like if it's not like close to zero, saying it's not some sort of metronome layer, this thing is much larger, which means yeah, it's much closer to AGC. Uh, but in the code, you can find that this weight part they also put in accumulated um, um, accumulated gradients, saying this is preconditions basically the square root of accumulated gradients, and this references is further references in the actual scaling back. So this is the scaling back. You can see the references. They actually have to sum up the all the references, which is the weights and the accumulated gradient step. And this is not how the paper describe it. Okay. So besides this, the position of the linear rate is also a little bit different. So I tried a lot of combinations to interpret like how it works, and I cannot make it happen nicely. Say, okay, so this thing is sorry, this thing is this is the AGC, which also works better, really awesome if you're thinking like it's just have huge loss or inaccurate in like a single one or two steps. Like if you look at this, like it doesn't impact too much as like it's much less than what if we doesn't design this kind of mechanism. And you can see this is very sensitive if one batch of the data distribution is really different. But for Clippy, for so far I cannot make it work. Even if like I take a look at their official data, official code deployment a lot. Like I refer to it like I try to change the code back and forth, but somehow it's still very hard to make it work. And of course and tomorrow this will be having a paper reading event, so I guess the personality who introduced this paper to us also said like he knows the person, one of the author that actually wrote the paper. I'm very looking forward to the answer, like why is there's discrepancy between the paper and the code, like how they actually deploys, and how far are my interpretation far away from the understanding of the paper. So I like this paper very much as it tried to solve that problem in very reasonable sense, like step by step, try to explain things the best they can, and they have their own perspective on like taking it looking at the problem, say, so they are trying to analyze why it happens in every detail, like every time they discuss something different. So yeah, I like this paper very much. And but maybe but still like a little bit failing to okay look at how the code works, because among their code there are also like a usual TensorFlow extra code on the optimizer, like lots of things, like how they are going to track all these scale factors and things, and they update things like this. Okay. Yes. So yeah. Let me look at my Clippy. Yes, my Clippy is isn't. I think it's not working very well. It's the measure is like I can see this spiking the measure as the measure will be triggered, but I cannot find a sweet spot that I can actually deploy the sigma. So for this sigma, oh, it's working. So for this sigma, you can see it's like hitting the roof here, but when the event of like a 1800 like this thing happen, it will be triggered. It's like it will be scaled back by that much, but it's not nothing like what's in the paper describes, but that's basically the idea. I will be publishing code somewhere in the link. You're welcome to experiments. This is a very fun reading and a very fun experiments of all things like so for this notebook, it will be trying to create a fake problems because actually set up a multimodal training is too much work for me recently. And this is a vanilla version of the undergrad, which I think is basically what the paper describes. Which will help us, better define our own version of the undergrad with the Clippy. So in my own Clippy, like this Clippy deployment is actually a optimizer. It's like I discard away the function that's going to update the gradients because it's not doing so. It's only scale back the updates, not the gradients. So you have to put it into the optimizer. This is exactly how the official code actually does it. It's like it actually published a Clippy article instead of a Clippy function. It also says when it's applying on the atom, it's also working, which is great news. So this method is pretty universal for the loss divergence problem. I don't know how it might work on game problem, which is also very notorious of for the loss divergence, like everything just explode and nothing goes back. Maybe this might work too, but I don't know like how it might combine to the training scheme yet. It also says like it's very much looking forward to like to see how this thing works, against other tasks, and lots of experiments still ways to be done. For me also, like I'm looking forward to it. Like anyone did experiments on this thing, please also comment and